All right, so a reminder that we have a quiz tomorrow to start off with, and then we'll be working on something for Thanksgiving. So y'all here that are here, be sure and bring your art supplies or whatever you like to be artistic with. And then at home, y'all will have y'all's out to work on that. So y'all will then have to, my virtual students, y'all will then have to take a picture of your product or scan it in and download it into Google Classroom at the end of Friday. We have short classes on Friday and we'll finish up what we start tomorrow. And then when we get back, probably have a test that Wednesday when we get back, but not right away on that Monday or that Tuesday. We'll take a couple of days. All right, let's look at this one real quick. See if my wants to catch up with it. All right, this one I had SO3. So all of those are from group 6. So I have 24 electrons. So that's what I have to start off as. I have to draw my structure before I can figure out what shape it is. So sulfur would go in the middle. And I would attach my 3 oxygen because that's going to be your first step was count up your electrons. Next one would be to put your least electronegative. And oxygen and sulfur are pretty close, but sulfur is a little less electronegative and it's listed first. And then I'm going to give my terminal or my outside atoms their octet. So that means I'm going to have to give each of the oxygen 6 more electrons. So once I've done that, that uses up all of my electrons, all 24, but sulfur doesn't have an octet. So I would have to donate a pair of electrons, and it could come from any of those 3 oxygen. They have a resonance structure. They all have the same number, so I would end up with sulfur, a double bond to one of the oxygen. And then all the rest would have their 6. So that's my correct structure. So from there, then I would say, how many areas of electron density or electron domain do I have? 3 bonds, so that means 3 areas. They're all bonds, no lone pair. So that's everything I'd have to kind of gather up. And then once I've done that, I would go to my little chart, which I think I still have open here. And then I would look to see what I have. We said we had 3 areas of electron density or domains, and all 3 of them were bonds. So that would give me a trigonal planar. So hopefully you were able to work through that. All right, today we are going to talk about ionic compounds, and they're different than the covalent compounds because they don't share electrons, they actually transfer electrons. So you'll need to go into your notes. We got just a little bit of notes to do. So we are on the front of the second page, Roman numeral 3. Where it says ionic compounds. And I know we've already filled some of this in. I'm just going to kind of refresh your memory here. All right. So an ionic compound is between a metal and a non-metal. Remember, your metals lose electrons and they become positive ions. Because that's what an ionic compound is. We're going to have attraction between positive cations and negative anions. My non-metals gain electrons and they become negative ions. And when they come together in an ionic compound, they should do so such that your positive and negative charges are equal. So in other words, you want it to overall be a neutral compound. And remember, this is not a molecule. A molecule is just whenever it's covalent. So we will not be using any of our Vesper geometry from yesterday because that's only for covalent compounds. And today we're doing ionic compounds. All right, so when we look at our Lewis dot, we have to think about the electrons actually being transferred. So sodium has 1 valence electron. Chlorine has 7. So when they come together, it works out perfectly that sodium can donate that 1 electron. So then the chlorine has a whole valence. And that sodium get rid of that 1 valence electron and fall down to a lower energy level that is complete. Once they have done that, lost or gained electrons, then they're going to have a charge. These ions should be in brackets, and the charge should be on the outside of the bracket. So since sodium lost 1 electron, it ended up with a +1 charge. Since chlorine gained 1 electron, it ended up with a -1 charge. So this would be sodium chloride would be the name of that. Remember, the metal stays the same. The ending of the non-metal is changed to "ide." And if I wrote the formula for that, that would be NaCl. Because for them to come together and be neutral, I just need one sodium for every 1 chloride, because they're equal to each other with opposite charge. When you write the formula, the metal comes first. So in other words, it would never be called chloride sodium, or you would never write it ClNa. Always does your metal first. All right, some characteristics of ionic bonding. It's favored that in such a way they will come together that the potential energy will be minimized. We've talked about that before. If there wasn't a reason for the elements to come together and lower their energy, then they would just say elements. They wouldn't form compounds. Like I said, we will not be using the molecular geometry because the ions don't do that. They form what's called a crystal lattice, which is an arrangement of ions in a way where the potential energy is minimized. And crystal lattices are alternating structures of positive and negative ions. So we know opposites attract. So when they line up, I'm going to have my cation, then an anion, then a cation, and an anion. And that would continue to replicate itself in that order. And we end up with what's called a crystal lattice. And the lattice energy is the energy released when 1 mole of that ionic compound is formed from gaseous ions. So it kind of tells you the strength of the bond. All right, so from here, we're going to go into our practice that we have today, and we're going to do some examples in there. So we have Lewis dot ionic compound practice, and that's what we'll look at. Some examples on that one. All right, bless you. We'll just start with number 2, and the first thing you would do is you would write the Lewis dot of the separate element. So lithium is from group 1, so it has 1 valence electron. And chlorine is a halogen, so it has 7. 2, 3, 4, 5, 6, and 7. So when they come together, the lithium gives up its 1 valence electron to the chlorine. So the chlorine has a full octet, and the lithium would fall down to a lower energy level. So now they're both going to be ions because one has lost electrons, the other one has gained. So I'm going to put my Li. It's lost 1 electron, so it would have a +1 charge. And then I'm going to take my chlorine, and it now has a full octet. Rodney, you don't want to write these examples down? No, Rodney, you don't want to get a paper and write them down? It's a lot easier that way on this especially.
I keep forgetting about these.
And because it gained 1 electron, it would now have a -1 charge. And it fit together perfectly. I got a +1, I got a -1. They cancel each other out. It's neutral. If I named it, it would be lithium chloride. The metal stays the same. The non-metal, the ending changes to "ide." And the formula would be NaCl. Because it's not Na. Let's try actually the right element. How about LiCl? Because for every 1 lithium, I need 1 chlorine to cancel it out. Okay. So that's kind of an easy one. They don't always fit together that perfectly. And we're going to look at some of those momentarily. All right. We good? All right. So let's look at one that doesn't come together quite so perfectly. I'm going to go down to number 5. All right. So I'll start my same process. I do the Lewis dot for individuals. So sodium is group 1. So it just has 1 valence electron. Nitrogen group 15. So it has 5. So the sodium is going to donate its 1 electron. But that only brings the nitrogen up to 6, and it wants to get all the way up to 8. So what do we need to add so I can have another electron to donate that nitrogen? I need another electron, and my other electron would be from another sodium. So I add another sodium. That fills up that spot. I'm up to 7. I need to get up to 8, so I need 1 more sodium. And then that will finally come in and fill in that last spot. So it took 3 sodiums, because they're each one will only lose 1 electron at a time. It took 3 sodiums to be able to fill up the octet of that nitrogen. So whenever I write them, I'm going to start off, I'm going to put a sodium. Each sodium loses 1 electron, so it has a +1. The nitrogen, it took a while, but it got all the way up to its octet, so I'm going to put 8 dots around it. And it gained overall 3 electrons. It gained 1 electron from 3 sodium. So overall it gained 3, so it would be a -3. I have another sodium. And another sodium. So if we look here, I have +1, +2, +3. So I have a +3 and I have a -3. So once again, they cancel each other out. They would be neutral. This would be sodium nitride. And my formula, I always write the metal first, Na, and because I had to use 1, 2, 3, it would be Na3, and then just N because I only needed one nitrogen. So for every one nitrogen, it's going to take 3 sodiums to cancel it out. So that's how you end up having subscripts on some of the compounds.
I got a question. What do you got those three items of sodium?
How do I have them? Well, it told me that what I was combining, sodium and nitrogen. If I did it with just one, that wasn't going to be enough electrons because that nitrogen needed 3 to get a valence. So I did one that only got me up to 6. So then I had to continue adding till I could get that octet. Your non-metal should end up with an octet 8. And then your metals are going to lose whatever they have on their valence. All right, we'll look at one more. Look at number 11. So I'm going to start the same way. My aluminum, group 13, so it has 3 valence electrons. And combine it with some sulfur. Wait, 6, thank you. 3, 4, 5, 6. All right, so sulfur needs 2 more. So it can get those 2 from my aluminum. But when I did that, it left my aluminum with 1 valence electron. I actually made it more reactive. So what do I need to add? My choices are either aluminum or sulfur. That's all I can do. Which one do I need to add? Another sulfur. Perfect. So another sulfur with 5. So that gives me a place for that last electron to go on my aluminum. But now I have this sulfur sitting here and it still needs 2 more electrons. So now what do I got to add? Aluminum. All right. I don't feel like I've done something. I'm missing something. I did 2 here. So here we're going to go 2. What am I missing up here? I feel like I'm counting something wrong. So for 1, 2. All right, I still got 1, so I need to add another sulfur, right? I'm good. Oops, too many. Because I still had this 1 electron sitting over here with this aluminum, so it still needed a place to go. So I had to add 1 more sulfur. 1, 2. Oh, did y'all see what I did wrong here? I went all the way back here as to where I did it wrong. Let me reverse myself. I knew I was off somewhere. When I put in this sulfur, the second one, I only gave it 5 instead of 6. All right. So my last aluminum went here. 7. So I'm going to need another aluminum. Because I still have 1 more place on that sulfur. So that second sulfur now has an octet, but once again, I got an aluminum hanging around here with 2. So what do I got to have? 1 more what? If I have 1 more sulfur that starts off with 6, it needs a place for 2 more to go. So here we go. 1 and 2. So now we finally got everything that we need. So I'm going to start off and I'm going to do my aluminum. And aluminum lost 1, 2, 3 electrons, so it's a +3. A sulfur started with 6 and it gained 2, so it's a -2. And then I got to find a place for my other ones. I got another aluminum. I got another sulfur. And I got another sulfur, and I'll put it on this side. Once again, you want to make sure that your positives and negatives are separated. So that's why I didn't pile all of my aluminum on one side and all of my sulfur on the other side. I need a positive to be next to a negative. So now if I check myself, 3 plus 3 is a positive 6. Minus 2 minus 2 minus 2 is a negative 6. So that would be a good formula because my positives and my negatives cancel out. Aluminum sulfide. And then what would be my formula? Al. I have 2 aluminum, so Al2S 2 3 S3. So that would be your formula for aluminum sulfide. So when you've done them correctly, then your positives and negatives should cancel out and it should be neutral overall. That's kind of the way that you would check yourself. So some of them fit together perfectly if they have the same charge. Some of them you have to do a little bit more work on. All right, so y'all got a little time to practice and give them a try. If you have any questions, and then just unmute yourself and ask them, and I can help you out if you need it.